Hello, my name is Simon Page. I'm a hydrologist with the Washington State Department of Transportation. I'm sorry I'm not able to share this with you in person. I'm going to talk today about WSDOT's climate adaptation strategies, which I call the highway to resilience. By now, I assume you have all heard about climate change, the anticipated changes in the seasonal distribution of precipitation, changes in the snowpack, and sea level rise. Like you, I frequently ask myself, what do these changes really look like on the ground? At WSDOT, we need to act now. We are designing projects today that we expect to be in use for decades to come. We can't wait for someone to tell us all the answers. To help find those answers, WSDOT has participated in 3 FHWA pilot projects to develop and test tools to identify climate vulnerabilities and adaptation strategies. I'm going to briefly summarize these pilot projects. The first pilot project involved getting our internal experts together with the University of Washington Climate Impacts Group and learning about the best available climate science. We used that science in conjunction with the knowledge of the boots-on-the-ground maintenance staff to identify where on every segment of the highway changes in weather, extreme weather events, or sea level rise would likely adversely affect the highway system. Once again, we were left with that lingering question, what does increased vulnerability really mean? We tried to better answer that question on our second pilot project in the Skagit Basin. We leveraged the latest two-dimensional hydraulic model that Corps had developed to manage flood risk on the Skagit River. Rather than simple polygons on a FEMA insurance rate map, the model could tell us the depth and velocity of floodwaters over the highway. We found that critical portions of the highway would likely be washed away, isolating portions of the community and leaving the hospital and island without connection to Burlington or Sedro-Woolley. With this vulnerability identified in much more explicit terms, we could move forward to identify adaptation strategies such as building new bridges, a causeway, segments of the highway to sustain overtopping, and cooperating with the county to identify alternative roads that could be improved to provide emergency access. Our third pilot project allowed us to compare and contrast the FHWA climate vulnerability tools with those tools being developed in the EU and evaluate a project that was in design. Our partners in the Netherlands were particularly interested in nature-based solutions. As a test bed, we used the SR-167 completion project located in Fife, Washington. This transportation project was conceived decades ago to move freight from the Port of Tacoma to SR-167 I-405 industrial corridor to the east of I-5. We have been working for about 20 years to develop a comprehensive riparian restoration program that will create thousands of feet of stream channel and restore hundreds of acres of wetlands and riparian forests along Hylebos creeks and its tributaries instead of conventional stormwater detention. We found that both tools were scalable and able to look at individual projects as well as networks of highways. These pilot projects were focused on planning processes. Let me summarize how we're incorporating climate change into our daily work, and then we'll move on to implementation on a project design. First, as an agency, we are committed to using the results of the vulnerability assessment along with the best available science to advance our plans and projects. Second, we are committed to sharing this information on our website and at gatherings like this. Third, we are sharing our system vulnerability with statewide emergency managers. And finally, we're using climate change science for asset management and project level design and environmental evaluations. Let's look at a real project and some of the analysis that we have done to make sure that the projects that we are designing are resilient. This first project is Glacier Creek. Glacier Creek is, as its name implied, fed by glaciers from Mount Baker. As I briefly highlighted previously, we're expecting the patterns of seasonal runoff to change with changes in the snow accumulation and melting. We are proposing a new bridge on SR 542 and are concerned that the new structures will be large enough to accommodate future flows. One of our consultants had developed a HEC-HMS model to evaluate an extreme flood event. I revised this model to have a finer vertical steps for the snow calculations and created 2 alternative hourly air temperature time series to present future conditions of a +5 degree Fahrenheit and a +9 degree Fahrenheit. This table shows the return interval flows. The first few columns are flows based on the USGS regression equations. The last three columns are the existing, the +5 and the +9 results from the HHMS model. Interestingly, the results are all about the same. I would expect the USGS numbers to be a bit higher, as it doesn't consider that a large portion of the watershed sees precipitation as snow. I dove in a bit deeper. This plot shows the annual peaks of the various HHMS model runs. As you can see, many years the results are the same, but sometimes peaks of the existing conditions are the greatest. I think this can largely be attributed to carryover in the snowpack. In the future, earlier fall precipitation events will occur as rain rather than snow and run off immediately. In the spring and summer, warmer weather will tend to lead to more melting of the snowpack, but there will be less carryover and reduced risk of large rain on snow events. Let's get back to the SR-167 project. Although we were designing the riparian restoration program to accommodate stormwater runoff without conventional stormwater detention, sea level rise really wasn't on our radar 20 years ago. As I was preparing my report, I looked at projected sea level rises, the emission scenarios behind them, and evaluated a range of sea level rises from 6 inches to 8 feet. I plugged those values in as starting water surface elevations for the downstream boundary conditions for our hydraulic models to evaluate all the crossings along Hylabos Creek. As I was preparing a draft report, Washington Sea Grant was preparing to publish a study with Island County to look at probabilistic sea level rise. Subsequently, Washington Sea Grant has published data and developed a website to look at probabilistic relative sea level rise along the Washington state coastline. The relative part considers tectonics, rebound, and other geologic processes that impact the elevation of the land surface. When you access this tool, you select a circle that best represents your project area, and you can download a spreadsheet that contains the projected sea level rise. As you can see from this example, you can look at the probability and a future date and look up the projected sea level rise. In addition, there's a similar table with the RCP 4.5 emission results and the likely ground surface change due to a large subduction zone earthquake. For every natural water crossing, we use the WDFW culvert assessment tool to evaluate the projected 2080 100-year flood flow. It works a bit like StreamStats. You use a map-based tool to identify the crossing, and the tool delineates the watershed and provides information about future flows. Although not required, we make design changes when practicable to accommodate these larger flows. Finally, I've attached some helpful links about climate resilience. First, there's WSDOT's climate change page, the FHWA resilience page, the UW Climate Impacts Group, and Washington Sea Grant's Coastal Hazards Resilience Network. Thank you.